Okay, we are talking chapter 2. Last time we talked about measurements, how to properly take measurements. Remember that when you do take a measurement, you want to make sure that you always look at the scaling on the piece of equipment. Really, there's two things, as we talked about, that you want to kind of look at. You want to make sure that you understand what each big marking represents. And again, as we talked about, that is, again, in this particular example, a 1 centimeter sort of difference. You also want to count the smaller markings, starting kind of right past that last big marking till you get to the next big marking, and that's 10 markings in this particular example. That means, like we talked about last time, in this particular case, that would be 0.1 of a centimeter. You could also take the smallest markings and divide it by 2. And that will give you your sort of precision, or how far you could take this sort of reading, which in this case would be really to the second decimal place. So remember that, there is some type of estimation. It always occurs in a measurement. So if somebody looked at this would be 1.1, 1.2. 1.3, 1.4, record maybe 1.46 centimeters. And remember that when we do take a measurement, we want to record all the certain numbers plus the first uncertain number. So these would be all the certain numbers. This would be our first uncertain number, our estimated digit, if you will. And really, those do make up sort of the significant figures in this measurement, which in this case would be 3 significant figures, where the uncertainty would lie in that last digit. And again, you could record it as 1.46 centimeters plus or minus 0.05 centimeters. Again, this really giving you how far you can take the reading. In general, you can take the reading to one more place to the right of the smallest marking is usually what you could do, not in 100% of the cases. I think we looked at an example the other day where you really couldn't go kind of one more place to the right. But in most cases, you can go one more place to the right of that smallest marking. We also talked officially how to identify significant figures. Obviously, any number that is a non-zero would be significant. In terms of zeros, any zeros that come before that first non-zero number are not significant. Any zeros that are trapped between two non-zero numbers would be significant. And our zeros at the end are really only significant if there is a decimal point in the number. Again, the decimal point does not need to be like right next to those zeros or anything like that, but it does need to be sort of in the number. Now, as we talked about, the estimated digit or the uncertain digit is always the last significant figure written, not necessarily always the last actual number that's written, although in a lot of cases it is the last number, but it's not necessarily the last number, but it should always be the last significant figure that's written. We also talked about scientific notation, where if you had a number such as this, remember that all those numbers that come before the times 10 part are always significant. And we can use scientific notation to sort of write as many significant figures as we need, because we can kind of control the number of significant figures when you do so. It's important when people sort of identify sig figs and it's written in scientific notation. Sometimes people make a mistake of putting the significant figure into a decimal and then trying to assign a number of significant figures, and you don't need to do that, because again, all the numbers up there should be significant before you do that. So for example, if we did have something like 2.70 times 10 to the 3, this would then go 2700, and they'll go, okay, it has 2 significant figures, and it really doesn't. It actually has 3 significant figures because it was written in scientific notation. So it's a very common mistake. Sometimes people will kind of do that, take the number out of scientific notation, and then kind of convert it into decimal form, and then count the significant figures. Any questions on any of that stuff we talked about last time, I think? Okay. So just kind of finish up a little bit about the significant figures. I know he went over it in lab as well, but just to make sure everybody's on the same page. There's also numbers that are considered exact numbers, which are numbers that are basically obtained one of two ways. Exact numbers are basically obtained through counting. So for example, if I had, some pens or something on my desk here, I'm not going to do any type of experiment to try to figure out, how many pens I have. I'm just going to simply count them. Or if I got the classic example of apples in a basket, I'm just going to count how many apples there are in the basket. I'm not going to find some type of experiment to do so. The other way that we find things that are considered exact numbers are really what are sometimes referred to as definitions or equalities. So definitions in chemistry are really equalities, like 12 inches is equal to 1 foot. That is what is referred to as an equality. It is two values that are on different scales but represents the same amount of something, and those are considered basically exact numbers. So what is the deal with exact numbers? The deal with exact numbers is this: they basically can have pretty much as many significant figures as you want to give them. Because of that, when we do calculations and we try to give our answer to the proper number of significant figures, we basically ignore anything that's sort of considered an exact number. If you're using a type of conversion that is an exact number, we really don't look at it to help us decide how many significant figures our answer should have. And there is a couple of exceptions where maybe we would look. If you remember, we talked about units as well, and there's really two types of units. There's really the English sort of units, and then there is the metric units that we come across. And if you're using some type of definition that is an English sort of conversion factor, that is definitely considered an exact number. You don't have to worry about it. If you're doing some type of metric to metric sort of conversion, that also is considered an exact number. You don't really have to worry about it. It's really kind of, technically speaking, when you cross over and you go English to metric or metric to English, however you want to think about it, you really should take into account the number of significant figures in that conversion factor. And how you would do that is you would do it based on conversion factor. There's typically always a number that is 1, and there's some other number. So there's usually a 1 number, and then the other unit is actually a number with some units. So you would look at the guy that's actually not 1 in that sort of conversion factor, and you would take into account the number of significant figures it has. There's a couple of exceptions where you would not do that, and those are the classic 1 inch is exactly 2.54 centimeters. I think they want you to also know 1 pound is exactly 453.6 grams. So these are sort of exact conversions. And technically speaking, you would not have to worry about the significant figures in those guys as you're doing a calculation. Maybe if you use 1 pound is 454 grams, which a lot of people do use, you might, technically is not the exact conversion, so you might want to look at it. So what that means is, if you do come across one of these conversions, and we'll look at it a little bit later, you want to look at those significant figures. I will say probably in most cases, it's not going to make a big difference. The answer a lot of times in a conversion problem is usually pretty much the original number. In most cases, not 100% of the time, but pretty close. Whatever the number of significant figures that original number has probably is kind of what you should shoot for there for your answer. And again, not 100% of the time, but fairly close to that. Any questions on that there? All right, so take a second here and how many significant figures each of these has. So reminder that always want to go left to right, and we really don't want to start counting until we hit the first significant figure, which in this case would be the 3. The 0 is trapped, so it would be significant as well, and the 4 is significant, so this first guy should have 3 significant figures in this case. Any questions on that? This is again a number that's written in scientific notation. So all the numbers there before the times 10 part are going to be significant. And again, we would not want to convert this into a decimal and then figure out sig figs. So we have the sig figs given to us here. This would be 4 significant figures in this particular case. 125, obviously they are all non-zeros. That means they are all significant in this case. In this particular case, we would start at the 1. And is that 0 significant? 0 is not significant. There's no decimal here. So this would have 1 significant figure. And lastly here, we would not start counting until we hit the 9. And the 0 is significant, the 2 is significant, and the 0 at the end is significant. So that is going to be 4 significant figures. Any questions on any of those there? All right. Here's just a couple examples of 2 types of measurements that we sort of come across. One here is a measurement, really, which is a measured value or an exact number. So obviously, a patient weighs 154, you would have probably weighed the person, so that's a measured value. If a basket holds 8 apples, that's something you would count. It would be considered an exact number. 1 kilogram is 1,000 grams. That's a metric to metric conversion, which would be considered an exact number. So again, we would ignore that when we're doing calculations. And I guess going from Denver to Texas there, 1,720 kilometers, which means that's probably was measured at some point to figure out the distance. So again, that would be a measured value. Let's talk a little bit about rounding. Normal rules for rounding is, again, wherever you're going to sort of stop in terms of significant figures for your answer, you want to look at the number to the right. And if it's 4 or less, we're going to just kind of drop all those numbers. If it's 5 or more, we're going to round up to give us the proper numbers. We never ever want to do any weird rounding. So I have 13,333 and I want 2 significant figures. What is the answer? $13,000. Anybody for 13? 13, let's look at both of these numbers. 13 has how many significant figures? It does have 2, right? 13,000 has 2 the way I wrote it, right? If I put a decimal at the end, it would not, it would have 5, but it does have 2. So they both have 2 significant figures, so they're good in terms of that. But we have to look at not really kind of changing the meaning of the number. There's a very big difference, right, between those 2 numbers. So if I owed you $13,333 and I said, hey, I'm just going to pay you 2 significant figures. Here's your $13. Have a good day. Probably not going to make it much out the door, I'm assuming at that point. But there's a very big difference between those 2. So we don't want to do that. So even though this has the right number of significant figures, it is definitely a different meaning. Now, if I say, hey, I'll give you $13,000, maybe give me the $333 teacher discount or something like that. You know, it's pretty much the same meaning. So it's a very common thing that sometimes people do is like, I gotta get the right sig figs, gotta get the right sig figs. They like lop off some numbers and go, okay, no, for sure, that's 2. So that's good. But you never want to change the actual meaning of the number when you're doing rounding. Any questions on that there? All right, so if we're gonna go 2 sig figs on these guys, looking at the first one here, our second significant figure would be the 5. So that would then look at the 7, which means we should round up in this case, and we should end up with 36 meters. Looking at the next one here, second sig fig would be here. We would look at the 2. Here we would drop the rest of the numbers. So this would be like a 3,800 grams. Should I put the decimal point at the end? I should not, because then it would be 4 significant figures, even though it looks more scientific, but not right in this situation. So we wouldn't want to leave it that way. And again, we wouldn't want to drop all those zeros because then we would change the meaning of the number. Here, second sig fig right there, we're going to drop 0.0026. And lastly here, this 2 be the second. In this case, we are going to round up because we are looking at an 8 that is next to it. So we end up with 1.3 kilograms. question around. Now, speaking of rounding, when you are doing calculations, it is probably good custom not to round too much until the very end. So you should definitely keep track of what you're doing. You should take a few more digits. Sometimes people call them guard digits, and they maybe put like a little line above a digit to know where the sig fig should end. I'm not a big fan, but some people do that. But you should really keep a few digits more than you should as you're going through your calculations, and really clean it up at the end. The reason for that is if you do a lot of really extreme rounding, not really extreme, but just rounding, and you get a number, and then you take that number and do another calculation, and you get that number and you round, and take that number and do another one and round. Every time you round, you're probably moving yourself further and further away from kind of the right answer. So it's really customary to sort of keep a good amount of digits. You don't have to keep 4 million digits on every number, but 2 or 3 past where it should be, and then kind of clean it up at the end. So try not to do a lot of rounding until the very end. So let's talk about calculations to make sure everyone's on the same page and what we should be doing. So there's really kind of 2 groups of calculations that we sort of do. We either multiply and divide, or usually we add and subtract. So in this case, if you multiply and divide, the answer you should end up with should have the same number of significant figures as the number with the least number of significant figures. So multiplying and dividing, you're looking at significant figures, and you're looking at the one with the least number of significant figures. So if you took 425 and divided it by 32, this guy has got 3 significant figures. This guy has got 2 significant figures, which means my answer should end up with 2 significant figures in this particular case. So multiplying, dividing, least number of significant figures is what you should look at. When you add and subtract, we're actually looking at decimal places here. So the number of decimal places, not significant figures, but number of decimal places your answer should have is the same number of decimal places as the number with the least number of decimal places. So once again, least, smallest, and the reason for that is, frankly, they are your worst measurements. So your calculation is only as good as pretty much your worst measurement. So we go with the smallest sig figs when we multiply and divide. We go with the smallest number of decimal places when we add and subtract. So if we had 4.25 plus 3.111, we add this 163, I hope 7. In this particular case, we would look at decimal places, and that is for the first number 2. That is 3 for the last number there, which means we actually should end up at 2 decimal places, and that would be 7.36 in this example, which is 2 decimal places. But how many significant figures? It has 3 significant figures, right? So it's important to keep that in mind, because you might take that number and then maybe do some multiplying and dividing, right? So you want to remember sig figs in decimal places. So multiplying and dividing, sig figs, adding and subtracting decimal places. They're both the least number in each of those cases. Now, if you do multiple things together, which does sometimes happen. So for example, if you had 325 times 12 divided by 4,659,69. What we would typically do first, right, is stuff in the parentheses. So technically speaking, we're multiplying. So we would look at sig figs. So the answer up on top, this guy has 3 sig figs. This guy has 2, which means for the answer technically that we should get from the top should be 2 sig figs. We then would be dividing that by our bottom number here would be our last step, which would be 5 sig figs, which means our answer should end up with 2 significant figures in this case. So if you're doing multiple steps, sometimes you do multiply, maybe you add first or subtract and then divide or multiply. You do want to keep track of everything, but again, I would avoid a lot of rounding until the end, but you keep track as you go through each step. And really your last sort of calculation that you do will kind of point you in, where you really should end up in terms of your sig figs or decimal places. Any questions on that there? All right, so let's take a look at some examples here. I scribbled apparently on the wrong page. So let's do that. There you go. All right. So for each of these, round these guys off to the proper number of digits here. Take a look here. So we are multiplying on the first one here. So we're going to look at sig figs. This guy's got 3. This guy's got 2, which means our answer should end up at 2. Here we look at the 7. We should round up. That's going to give us a 9.4 as our proper digits. Looking at the next one, we're dividing. So once again, sig fig. So this guy's got 4. This one's got 3. So we're going to 3 sig figs, which actually takes us to the 8. Looking at the 2 there, we're just going to drop the rest of it. So 0.0758 would be here. Any question on those 2? Coming to our next one, we're doing a little addition. So once again, here we're going to look at decimal places. So that is 2 decimal places. That's 1. That's 3. That means the least number of decimal places is 1. So that should take us to 29.1 in this particular case. And last, we're subtracting. So once again, decimal places. So that is 4. That is 1. Taking us here to the 5. So look at the 8. So we do need to round up. And that would give us 0.6 here in terms of our answer. Any questions on any of those there? A reminder that obviously your calculator does not give you your numbers and the correct number of significant figures, right? So make sure you edit yourself as you look at the calculator to the correct number of significant figures. And a way not give you your answer in scientific notation if you're looking for that, unless you programmed it to do so. So keep those in mind. Any questions on calculations? Figuring out sig figs. Any questions on any of that? Just to finish up a little bit about some of these measurements that we were talking about. I think we talked about the other day, some of these prefixes that we use to change metric numbers. And a reminder, you should know some of these, that when you look at these type of tables or values, this is how much there are in the base unit to one of the prefix units. So again, if you look at kilo, which is 10 to the 3, 1 kilogram would be 10 to the 3 grams. 1 kilometer would also be 10 to the 3 meters. It doesn't matter the base unit, as we talked about. Again, people very commonly reverse those and get them incorrect. 1 centimeter is 10 to the minus 2 meters. How you get sort of the other numbers is you can divide 10 to the minus 2 to the other side, and you'll get like 100 centimeters is 1 meter, which is the same conversion. It's a little bit different. So a reminder that kilo, deci, centi, milli, well, ones you should probably know do come up a lot as you go into 1A. These 2, micro and nano, do pop up a lot along the way. Any questions on how to use those prefixes correctly? All right, so just to finish up some of these ones we talked about last time, some of the common units we do come across, I would say definitely these 2. 1 meter is 100 centimeters, 1 meter is 1,000 millimeters. I would definitely say in terms of volume, our 1 liter and 1,000 milliliters is one that we come across a lot. And again, you should definitely know that one. We also talked about our cubic centimeters last time. That 1 cubic centimeter, which is a volume, can be found by taking the length times the width times the height. If each of them are in centimeters, that is how we get to our cubic centimeters, which once again is a volume. Each of the individual measurements, again, are length measurements, but that is a volume. So definitely the 1 cubic centimeter is the same thing really as a milliliter. I would say milliliters are used a lot, obviously, when we measure out some type of liquids. Cubic centimeters are used a lot sometimes with solids, kind of like what you did in the first experiment where you took the wood block and measured in 3 different sort of directions to get the volume. And you'll do again today. We also talked about the meniscus, right? You always want to read from the bottom of the meniscus when you do take the measurement. And by the way, this would be one scale where you could not go to one more place to the right. The big markings represent 10 milliliters in this case. There's only 5 markings between them, which means each little marking actually represents 2 milliliters, which means if you took 2 milliliters divided by 2, the best you could do in this case is plus or minus 1 milliliter in this particular case. Again, this first marking here would be like 82 and 84, 86, and so forth as you go there. So really important to always look at the scale. It's not always what you might think it is, as you might have saw with the different graduated cylinders as well in that experiment. Even though they're all graduated cylinders, they all have a different sort of scaling on it. You want to make sure you know how to properly read them. Any questions on that there? Obviously for mass, I would say these two are very common as well. 1 kilogram is 1,000 grams and 1 gram is 1,000 milligrams. All right, so I think what we're going to do is actually we're just going to skip ahead and we'll come back to what we're going to talk about is actually density. If it comes up, there it is. And again, these are your notes just a little further down towards the end. So density is the mass of a substance over its volume. And it does have a formula, D is equal to M over V. Common units of density are grams per milliliter, are grams per cubic centimeter. And once again, that should be like a cubic centimeter. For liquids and solids, we don't really get too much into it in here, but for gases, a lot of times density is given in grams per liter. If you take 1A, you will in the gas chapter figure out how to calculate the density of a gas, and usually they are reported in sort of grams per liter. But for the most part in this class, grams per cubic centimeter, grams per milliliter are the two that we see. And as we talked about a second ago, a milliliter again is equal to a cubic centimeter. This is a formula which you could rearrange. So if I want to solve for volume, that would be mass divided by density. If I want to solve for mass, that would be volume times the density. Then obviously our density is mass over volume. Sometimes people remember this by everybody's favorite place, the DMV. The DMV triangle. Density is mass over volume. Volume is mass over density. And mass is density times volume. You definitely need to know how to rearrange. Obviously, this formula, we do solve for any of these sort of variables along the way. In this case, in terms of the units, they really don't cancel out because up on top is mass, which is a different quantity than volume. So grams and milliliters will never cancel out. The number always stays with the grams part, and the volume is always really 1. So if you did have a density of a substance, say that was 1.45 grams per milliliter, you could really use it as a conversion factor, 1.45 grams per milliliter. If you needed to kind of divide by it, you could flip it around and really use it as a conversion factor as well. So sometimes we use density as a conversion factor to do dimensional analysis sort of problems that involve density. The density of an object determines whether or not something will sink or float. So for example, right, if something is more dense than liquid water, it will sink. If it is less dense than liquid water, it will float, right? So, for example, if I took a can of regular soda and a can of Diet Coke, will they both sink? Will they both float? What will happen if you throw them into like a bucket of water? Well, it's a good trick, but the Diet Coke will actually float, yes, and the regular Coke will sink. And that's because in regular Coke you have sugar, right? Heavier than the artificial sweetener that's in Diet Coke, for example. So it actually lets it float. The regular Coke sinks. I know, good party trick in case you're getting together with people. You know, you can try these things. All right, so let's try an actual calculation here. A block has a volume of 25.3 cubic centimeters. The mass is 21.7 grams. Calculate the density of the block. All right, so if you're not sure, obviously density is mass divided by volume. So clearly we have a volume here. So we have that. We do have a mass as well. So really in this case, all we have to do is plug and chug into here. So that's going to be a 21.7 grams divided by 25.3 cubic centimeters. And if you do that, 0.858. Again, the units do not cancel, so it'd be grams per cubic centimeter would be our answer. Again, the number stays with the grams, 1 cubic centimeter. Significant figure wise, we're dividing. So we're looking at sig figs here. So that's 3 sig figs on top, 3 sig figs on the bottom. Our answer should have 3 significant figures when it's all said and done. Any questions on that one there? By the way, in general, if you ever need the density of water, liquid water, most people will use the value of 1 gram per milliliter. You should note that density actually does change with temperature. So depending on the temperature, it might not really be the accurate number, but I would say in most sort of textbook problems, you ever come across a place where you're like, I think I need the density of water, 1 gram per milliliter is usually the value that most people will use, although in reality, it does change with temperature. All right, well, we try another one here. Actually, let's talk about another way that we can get volume. So there's really sort of 3 ways that we can kind of get the volume of a substance, 2 of which we've talked about, which is obviously we could just simply put a substance into something like a graduated cylinder and actually take a reading like you will do today in part 1 and 2, I think, of the experiment. The other way is we have some type of solid like we had the other day and also today. You could do your measurements of your length times your width times your height, which once again will get you your volume in something like your cubic centimeters. The third very common way that we get a volume, especially dealing with density, is volume by displacement. And volume by displacement is an idea of you take a container, for example, and you fill it up with a liquid like water, and you take an initial reading, and then you put some type of solid in there. So you take some type of initial volume reading, you take a solid and you dump it in there. And when I dump the solid into my graduated cylinder here, will the volume level go up or down or stay the same? Should go up. So we will see the volume level actually increase. That is the displacement we're talking about. It will actually displace a volume equal to its own volume. So it's a very convenient way for solids that you can just drop it in some water and figure out the volume of it. And you would take a final reading like you will do today. And if you basically take the difference between those two, the volume of the object would equal the final volume minus the initial volume. So that's a very, very common way in chemistry to figure out the volume of a substance. Is to do that, just basically take some liquid, take a reading, drop the solid in there, take the next reading. And that's what we see here. Before she dives into the tank here, the water levels at a certain height. Once she goes in, the water level is displaced. And again, if we take the difference between where she started and where the water level basically ended up, that would represent the volume actually of her as she goes in there. Hopefully those are not just markings, but also a ladder so she could get out, or she could hopefully hold her breath a long time, one of those two. But again, a very, very common one. I think you do this in part B of the experiment today. Fill up a graduated cylinder with some water, drop a stopper in there, and then take another reading to get the volume. Any questions on that there? All right, so why don't we try one here? Student fills a graduated cylinder with 25 milliliters of a liquid. She then puts a solid into the liquid. The volume of the liquid rises to 33.9 milliliters. The mass of the solid is 63.5. What is the density here? Let's take a look. So once again, we are looking for our density, which is our mass divided by volume. This is basically the same situation as I drew earlier. We got a sort of graduated cylinder, has an initial volume of 25 milliliters. We're going to put the solid in there. Volume is going to jump to 33.9 milliliters. So obviously this is how we're going to get our volume that we need, which is the volume by displacement. So the volume of the object in this case would be our final volume, which is 33.9 milliliters, minus our initial, which was 25 milliliters. And that's going to give us a 8.9 milliliters. In this case, we have the grams given to us right off the bat here. So the density in this case then would be 63.5 grams divided by 8.9 milliliters. And that's going to get us 7.1 grams per milliliter. First off, any questions on the calculation? Why is it two significant figures? Is two significant figures based off of the subtraction we did first. We would go to decimal places, which takes us to one decimal place. 8.9 is one decimal place, but two significant figures, the very significant figures divided by two significant figures gets us to two significant figures when it's all said and done. Any questions on that one there? Yeah. It is. So typically when you have two units for an answer, typically the numerator gets the number and the denominator is usually like per one. So that's usually how most people would write it. Some people might even write it 7.1 grams, big line underneath that, and milliliter on the bottom. But you just want to note that the number should go with the top unit and the bottom number is usually one. We never ever usually will leave an answer in a fraction where they both will have numbers. So you should always kind of divide out the bottom number, which means the bottom will always end up as a one, and top number should always end up as a whatever the number may be. Other questions? So here's the density of certain substances. And again, as I mentioned, the 1 gram per milliliter cubic centimeter is typically the one most people do use for water. Although water is an unusual substance, the fact that the solid version is actually less dense than the liquid version. That's why when we put ice in our drinks, right, it ends up floating to the top, right? And ice is the liquid, it's the solid version of water. And it's actually less dense than the liquid version. And that's an unusual sort of characteristic. As we'll talk about in a later chapter, the reason for that is as all the water molecules basically come together in the solid state, they create a lot of open volume between the different water molecules as they come together, which if you think about density, which is mass divided by volume, if it creates this open volume, much larger volume right on the bottom when you divide, big number on the bottom, smaller number up on top, gives you a smaller density value for ice than you see in liquid water. All these guys here, which obviously has a value greater than 1, would obviously sink in water. And obviously things below it there would actually float in water. Obviously, if you put two liquids together, like water and something else there that has a smaller density like ethanol, what will happen when you look at it, say in the test tube, put two liquids together for densities? They will separate out based on sort of layers, right? And the more dense would be at the bottom, right? Less dense there would be towards the top. If you threw something in there and it just kind of stuck right there in the middle, and that's layer, that would tell you that it is obviously less dense than what's below it, right? But more dense than what is above it, right? Also a nice party trick as well, in case you're doing those things. They will technically, they will actually mix together and make one layer. So ethanol maybe was a bad example, but something maybe like benzene or something like that, which obviously won't mix together. There's other factors that will allow them to mix ethanol and water due to hydrogen bonding. So not the best example there, but something else that's obviously less dense than liquid water would layer out, or if you had different just liquids at different densities, they would layer out. Other questions? All right, so let's take a look at another example here. A student needs 150 cubic centimeters of salt for an experiment. The density of salt is 2.16 grams per cubic centimeter. How many 1 pound boxes of salt would they need? By the way, 1 pound is 453.6 grams. All right, let's take a second or two, see what you come up with. You can see how we're doing. So in this particular case, we have 150 cubic centimeters. That obviously is a volume. We have the density given to us, which is 2.16 grams per cubic centimeter. And once again, you can use density as a conversion factor, so you can kind of flip it around if you needed to maybe divide by it and sort of use it that way. In this particular case, obviously we're dealing with density here. If you're not sure, we obviously have the density and the volume given to us, so it would make sense to solve for mass, which in this case, mass would be volume times density. Remember that we do want to show sort of our calculations with the units and the units canceling, which is dimensional analysis. So if we take that sort of approach, we would start with 150 cubic centimeters. When we do something like dimensional analysis, what we're doing is really canceling out the units. And it's really like fractions is basically what we're doing. So in this case, although the cubic centimeter is not really written as a fraction, this cubic centimeters are kind of like up on top. So to get rid of them, we would want the opposite location for the cubic centimeters, which would be that. And we would go with the 2.16 grams per cubic centimeter. The cubic centimeters in this case would actually cancel each other out because we're dividing by them. So again, it's kind of the same idea. If you took 2 divided by 2, it would equal 1. If you have cubic centimeters up on top and cubic centimeters on the bottom, it actually cancels each other out basically and equals 1. Mathematically, what we're doing is basically multiplying whatever's on top and would be coming back and dividing by what's on the bottom, which in this case, there's not much on the bottom, but if there happened to be a number, we would divide by what's on the bottom. In this case, if we just multiplied the 150 times the 2.16, leaves us with 324 grams of salt is needed. In terms of significant figures, what should it be in this case? Should really be 2 significant figures, which would take us to here, which would be about 320 grams of salt would be needed, as this is really 2 sig figs. This guy is 3 sig figs, and we're multiplying basically here. So we would look at significant figures for our answer. And we also want to make sure that we always answer the question, which means in this case, we would actually just need 1 box of salt. Right. You would have some left over to share. I don't know why you're bringing your own salt to school, but you know, you would actually just need 1 box, since 1 box obviously is 453.6 grams. Any questions on that calculation there? Question on density. Obviously, you need to know the formula, and you know how to rearrange it. You need to know how to solve for density, volume, or mass. You know how to obviously get the volume from reading the volume, get the volume from length times width times height. And obviously get the volume from volume by displacement. Any questions on any of that there? Okay. We did that. The last thing we're going to kind of talk about in this chapter is really a really important sort of technique that obviously you should learn in this class. They expect you to do these calculations, as I mentioned earlier, I think the other day. You know, they want you really to show all your work through what is known as dimensional analysis, which we're going to talk about. But it's basically what we just did there in that last problem, where you show all the units, you show the proper conversion factor, you show the units canceling. That's really sort of, you know, how they want you to kind of set everything up. In order to do that, we use equalities, and equalities are really two values that are on different scales, but represent the same amount of something. So if you had 100 pennies, that would obviously represent $1. You had 12 inches, would represent 1 foot in this particular case. So again, these are what are known as equalities, and basically from any equality that you come across, you basically can write two conversion factors, and basically the two conversion factors are really just the fractions from these guys. So for example, here we could write there are 12 inches and 1 foot, or the other conversion factor would be 1 foot in 12 inches. In most problems, you definitely do not use both conversion factors. Otherwise, you probably undid your calculation by reversing it. But we do use obviously whichever one would get us to our final sort of result. So let's say we had 125 inches and we want to know how many feet that was. We again would take the dimensional analysis approach, where we would want to use the conversion factor that has the unit we want to get rid of in the opposite location. So once again, the 125 is not really written as a fraction. The inches units are up on top. So to get rid of the inches units, and all sort of conversions, they're always opposite. So we want to put the 12 inches on the bottom and the 1 foot up on top. Once again, in this case, the inches would cancel, and we would take 125 divided by 12. Gets us 10.41. We'll call it 667 at some point. Feet would be the units that are left here. Now, once again, we are multiplying what's on top. We're dividing by what's on the bottom. In this case, we want to look at significant figures for our answer. So pretty much in any type of dimensional analysis problem, you're pretty much multiplying and dividing. So it's all about sig figs is pretty much what you want to look at, like we talked about. In the case of this guy here, this is basically one of those exact numbers. So again, that's that definition. It's an English to English sort of conversion. So that is an exact number, which means pretty much when we go to figure out our answer, we're just going to ignore its contribution, because frankly, they could be as many as you want. So we're not going to look here. So that really does, in a lot of conversion problems, leave you kind of like the original number. And the original number here is 3 significant figures, which means our answers should end up being 3 significant figures. So in this case, it would end up being 10.4 feet would be our correct answer here to the correct number of significant figures. Any questions on that there? Yeah. Yes. Yeah, so they definitely, and I'm saying yes because like I said earlier, I think on the first day, right, they're really stressing how they want you to do these problems, because most of you are going to continue on right to 1A and 1B, and they're going to like yell at you and maybe take out points if you don't set it up this way. So they definitely want you, in terms of pretty much most problems outside of maybe it's like the density one, maybe where you just kind of have the mass and the volume just divided out. They do want you to kind of show all the work in the dimensional analysis with the units and stuff like that. So with that being said, there's definitely many different ways you could kind of do it, right? But for here, you got to set it up that way. Again, just to hopefully set you on the path for success, so you don't get shocked when you roll into 1A and stuff and they start like Who taught you how to do these things, right? You know, you're not doing it correctly. Yeah. Yeah, so the deal is there's really two types of numbers. One is an exact number, which basically is one of two things. Is either something that really isn't measured, it's just something simply counted, like the apple example or the pence. The more common place where we come across exact numbers are through equalities, or and they're sometimes referred to as definitions. So like the 12 inches is 1 foot is considered an exact number. Whenever you have an English to English conversion, it's definitely an exact number. Whenever you have a metric to metric conversion, like kilograms to grams, for example, that is an exact number. It's really only time you have to worry about it is when you cross over from metric to English. You do have to look at those conversions, and in most cases decide whether or not, you know, you should take them into account. Now, in most cases, in my experience, and again, not 100% of the time, but in most cases, even if you did take like an English to metric into account, a lot of times your original number still has less significant figures in most cases, a lot of times. So you usually are good to go back there. But to truly answer your question, exact numbers, because they're based off of definitions and stuff like that, technically could have an unlimited number of significant figures. Technically, they could have, like I could go, hey, I want that guy to have like 5 significant figures. You could go, nah, I think it should have 3. And somebody else could go, I have 2. And it would be acceptable because they're exact numbers. So they have an unlimited number of significant figures. Because there's such variation that could occur, people try to use those in calculations. What we typically do is just ignore them, because again, I might go 5, you might go 3, somebody else might go 2. So if it is an exact number, it's ignored in terms of how many significant figures your answer should have, because of that variation that it could have. You would not in this case, because we would ignore this, and that's the customary way when you're doing calculations like this. You would ignore its contribution, but you still have this number, and this number you would not ignore. And this number has 3 significant figures, which is why your answer should have 3. And that's why I said earlier, you know, if you want to be right more times than not, whatever sig figs this guy has, probably is what you should end up with. Again, not 100% of the time, but in a lot of cases, that's what ends up happening. Other questions on that? Yeah. It's always opposites. I won't always say it's going to be opposite on the bottom, because you could have 2 units you're starting with, right? And you may have to change both of them. So it's really opposite locations. So if it's on top, you got to put the same unit on the bottom to cancel it. If the unit happened to be on bottom you want to get rid of, you got to put that same unit on top. It's like any math operation, right? It's always opposite, like when you go across an equal sign. So if you're multiplying on this side to get rid of somebody, you got to divide it. It's kind of the opposite sort of process, and that's what happens here. Same thing if you're dividing on one side of the equal sign, multiply to get rid of something, right? So it's sort of the opposite, and the same thing here with the units. Opposite locations will cancel. Other questions? So that's sort of what I talked about in terms of the dollar. Let's take a look at some common equalities. And again, here, this is really English to English to US. So these all would be considered really exact numbers. So if you use any of those in a calculation, the beauty of that is you don't even have to worry about it. You don't have to consider them in terms of significant figures or anything like that. If you use any of these guys, which are metric to metric, again, those would be considered for sure exact numbers. You don't have to worry about them in the calculations or anything like that. I will say again, a reminder, inches to foot, I hope you know. Feet and miles come up a lot. So that's something you should be aware of. I would say that you should know, I hope, 16 ounces in a pound. In terms of here, these guys do come up a lot. Our milliliters and liters, our cubic centimeters. And then I would say these guys in terms of that come up a lot. This, I hope you know, yes, right? There's how many seconds in a minute? 60, yeah. How many minutes in an hour? 60, how many hours in a day? It's 24, not 60. I can't tell you how many people I've seen go 60 hours in a day. 24 is plenty. Yeah, so keep that in mind as you go through it. Now, as we talked about, when you get to this column here, technically speaking, these are not really exact numbers. So you should take these into account as you're doing the calculations. The one exception would be this guy. And really, not really this way, but the 1 pound is the 453.6 grams would probably be another exception. But again, if you're kind of doing something like this, kilometers to miles, for example, that's sort of English to metric conversion. What we would use in terms of conversion factors is 1 kilometer is 0.621 miles, or 0.621 miles is 1 kilometer. Now, let's say we use this in a calculation in our dimensional analysis. We would look at the significant figures here. We would not look at the significant figures with the 1, because obviously in most cases, what I was talking about earlier, there's always one that's 1. So we would look at the significant figures here in this actual number, and we would count it as 3 significant figures in this case. So if you were using some type of metric to English, you would look again, not at the 1, because they all will have a 1 is equal to something, but you would look at the actual number and count that as 3. Now, again, in my experience, not 100% of the time, but in a lot of cases, this will sometimes have usually more significant figures than your original number. So, but you should look at them just to make sure. Any questions on that there? All right, so a couple examples of writing conversion factors from equalities. 5,280 feet equal 1 mile. We obviously could write 5,280 feet over 1 mile, or 1 mile is 5,280 feet. Now, sometimes we do end up with a couple of units, as sort of was the earlier question. Whenever you have something per something, like miles per hour, that's basically a fraction. That's basically 2 units. So if you're driving 65 miles per hour, that basically means you could go 65 miles in 1 hour. If you're on cruise control and the freeway is not washed away, you could do all those things. Or you could say 1 hour is 65 miles. So we sometimes do have multiple units that we might need to convert. Maybe you want to know, instead of miles per hour, how much kilometers per second that is or something, right? So there could be places where you might need to convert both of the units. If we were doing something like kilometers per second, you would have to do a conversion where miles go to kilometers up on top, hours go to seconds on the bottom, and setting it up with that dimensional analysis where you can see the units cancel is really a good way not to lose units. So very commonly, when people don't set up dimensional analysis and they do run into something like that where they have multiple units they want to convert, they end up not knowing if they should multiply or divide. So setting it up like that allows you to clearly understand if you should multiply or divide. 91 octaves, 305 a gallon. I would like to go find that these days, I suppose. As sad as it sounded when I wrote this, that was expensive at 305 a gallon. Now we think we'd take it in a heartbeat. So that means basically every gallon of gas is 305, or $3.05 will get you a gallon of gas. Well, at least I'm not super old. It didn't say like 79 cents per gallon, right? Another very common sort of values that we want to kind of convert into kind of conversion factors is a lot of times percentages. So whenever you have a percentage, it's very easy to kind of convert it into a conversion factor by assuming really that you have 100 of something. And the reason we assume 100 of something, it keeps the numbers the same, basically. So if you got 80% on your exam, you got 80 out of 100 probably, right? So it keeps the numbers all the same. So in this case, if we had 12% body fat by mass, we could do kilograms, which is a common unit of mass for people. That would be 12 kilograms of body fat per 100 kilograms of body mass. Or again, we could flip it around and use it the opposite way, 100 kilograms up on top of body mass, 12 kilograms of body mass. We could also do more of an English or US sort of conversion, 12 pounds of body fat per 100 pounds of body mass, or flip it around, 100 pounds of body mass to 12 pounds of body fat. So the idea behind how you should set up all these problems is dimensional analysis. And it really is, for example, if you had an equality like unit A equals unit B, and maybe unit B equals unit C, what we would do if we say started with unit A, we would use this as to make our conversion factor. And as we've been talking about opposites, so unit A is up on top, we would put unit A on the bottom so that it cancels. Unit B up on top, these guys would cancel. If I stop right there, I'm at unit B, which is close, but maybe I want to go to C. So we could just continue on the calculation. So by setting it up like this, you could clearly see that my unit B is still up on top, which means to get rid of it, I got to put unit B up on the bottom. And I can use this for my next conversion. Unit B on the bottom gets me to unit C. And these guys would cancel and leaves us with unit C in this case. So by setting this up again, this way you can see all the units. You could also understand, should you be multiplying, should you be dividing? Once again, we are multiplying everything that's up on top. We're coming back and dividing by everything that's on the bottom. That's basically what we do. I will say calculator note here would be, if you have multiple sort of conversions that are set up like this, people want to push it all into their calculator all at once. And once again, if you are not good with parentheses, you will get the wrong answer. So the safe thing to do is you can multiply as many numbers as you want on top, hit equal, come back and divide by the first number, hit equals, come back, divide by the second number, hit equals, and keep hitting equals. You will probably always get the right answer in that case. But if you try to put it all in at once, there's a good chance you'll probably end up with the wrong answer. Any questions on that there? So let's talk about the steps to dimensional analysis and a good way to kind of go through these problems. A lot of times it's good to write what's given to you and also what you're trying to find. You then want to write the appropriate equalities and obviously the conversion factors that go with it. And really for our purposes here, number 5 is what you got to show, which is the setup where all those units are canceling out like we did in a couple of those examples a second ago. And you should obviously solve the problem to the right number of significant figures. Again, in dimensional analysis problems like this, for the most part, you most likely will be multiplying or dividing, which again means when you get to the answer at the end, you're going to be looking at sig figs. And in most cases, the kind of middle part of the calculation where you're using those conversion factors, a lot of times those are considered exact numbers, so you don't have to worry about it. So, again, only if you got that metric to English, you should take a look at it. But other than that, you should probably be okay. Do you need to show all these steps? And we'll go through a problem probably next time since we're running out of time here. You don't need to show all the steps, but you definitely do need to show that 5th step where you show all the setup. So that's really important. If it helps you to write out the equalities, conversion factors, you should do so. If not, you just got to show the main work there. Any questions on any of that there? Okay, we will lay it up, I think.